Thank you very much. The title. So the main thing I want to talk about is a certain relationship between Borel equivalence relations, the study of Borel equivalence relations up to Borel reducibility, and the study of symmetric models and fragments of choice, where the main point will be a certain way to, a specific way to translate questions about Borel reducibility to questions about symmetric models. But let me start with telling you what kind of questions we'll care about in the realm of Borel equivalence relations. Should be a little bit of a long story. So a few basic definitions, which you've heard some of them. So the Friedman-Stanley jumps. The first Friedman-Stanley jump, which we will call congruent sub 2, which is also called equality plus, which was on Tuesday called F2, has many names. So it's an equivalence relation on R to the omega, defined so that this map completely classifies the classes, meaning that two sequences are equality plus related, even only if they enumerate the same set of reals. So it's very defined so that this is a complete classification. Invariance here is, well, our countable sets of reals, which I wrote as sets of integers to see where this sub 2 comes from. So it's okay, and similarly, the higher Friedman-Stanley jumps, for each countable ordinal alpha, there's this congruent sub alpha equivalence relation, which I'm now not telling you really what it is, but it's some equivalence relation that can be naturally classifiable, that is classifiable by hereditarily countable elements in the alpha power set of the integers. It might be a bit vague, but for today, we really will only care about the definable invariance rather than the Borel structure of the equivalence relation on its domain. Okay, so some more definitions. Let's say, so we have an equivalence relation on some polyspace X, and we assume it's a Borel subspace set of X cross X. We can try to measure the complexity of E in terms of the Borel complexity, right? F sigma, G delta, whatnot. The notion of potential complexity is just the closure of this idea under Borel reductions. So an E is potentially gamma for some point class gamma if it's Borel reducible to an equivalence relation which is in gamma. So it's simpler than an equivalence relation which is gamma. So example, right, the equality on the reals, it's the diagonal, it's closed, but it's not potentially open because any open equivalence relation has just countably many equivalence classes. So it's not reducible to an open equivalence relation. So in this case, we say that pi 1 is the potential complexity of equality on the reals. And generally speaking, if we can find this kind of point class that is the minimal one, such that E is potentially gamma, we say that gamma is the potential complexity of E. So let me show you maybe more concrete examples of it. So in this paper from 1998, Hjorth-Kechris and Louveau, they studied Borel equivalence relations which are induced by closed subgroups of S infinity, where S infinity is the Polish group of all permutations of omega. So this class is also known as the equivalence relations which are classifiable by countable structures, the same, but just the Borel ones. And they completely understood what are the possible potential complexities of such equivalence relations. So what I mean by this picture is any point class that is not in this picture, they have a theorem of the form it's not the potential complexity of something. So if E is potentially sigma 4, then it's actually reducible to something simpler than sigma 4. So D is the difference class. So D pi 3 is a set is D pi 3 if it's the difference of two sets which are pi 3. So it's the first, so one of the surprising things is that there are so many things that are gone, right? All the sigma 4, sigma 5 are all gone, and all the difference hierarchies are also gone, just the first one is left there. So they kind of get rid of them all. And then, so that's a lot of work, and with whatever is left, they find examples of such equivalence relations, and in fact, they find maximal elements. So what I mean in this picture, for example, is that for any E that satisfies this, if it is potentially pi 3, then it is reducible to equality plus. So, and similarly, and okay, they also show that equality plus is exactly the potential complexity is pi 3, and it's maximal. Friedman-Stanley jumps exactly correspond to all the pi classes. So, and right, so you see there's a pattern here. Of course, it goes all the way to omega 1, and the pattern is a bit weird at the beginning, but then it's consistent. Other than the funky stuff at successor to limit stages that all of a sudden one sigma appears. But the point is that for the rest of these classes, the difference classes and the sigma omega plus 1, there were no known example of equivalence relations with that potential complexity. So they defined something, and that's going to be the next definition. So I'm just going to define more relations to fit in those potential classes. I guess you see this. So there's this weird doubly indexed congruent star equivalence relations, where they're only the maximal one. So for each alpha plus 1, which might be 4 here, there's this hierarchy, small hierarchy converging to it, where the maximum index on the right is, I guess, n minus 2. Let me only give you the definition for 3, 1, and the rest will be kind of similar. And again, I will only give you the definition. I will only tell you what are the invariants that correspond to this equivalence relations. So which is already somewhat long, but so an invariant for star 3, 1 is, first of all, is a set of sets of reals. So something that looks like it's an invariant for this second Friedman-Stanley jump, this congruent sub 3. So yeah, the complexity should increase with on this picture here on the right. So the point is that it looks like a complicated invariant for this congruent sub 3. It's a set of sets of reals, but there's some simplifying assumptions that there is a definable relation, relation R definable from A, that whenever we plug in an element from A in the relation codes an injective map between A and the reals. So the point is that it's a set of reals that uniformly definably uniformly in a parameter from A, we can find injective maps from E to the real, therefore code it as a simpler set, just a set of reals. And it's not definable, but it is definable uniformly in a parameter, and the parameter is important. So for example, so maybe it's some sort of higher analog, you can think of it as countable equivalence relation. So for example, if you have the Vitali equivalence relation, what is the class? It looks like a set of reals, so it might be like a equality plus invariant, which is complicated, but in fact it's simpler, because if you look at a class of the Vitali equivalence relation and you fix a parameter, an element there, then the rest can be definably enumerated just using adding rationals, right? So it's some similar things, just higher analog options. So this was the 1 here, and if we replace the 1 with a 0, the invariants will be sets of reals, which definably uniformly in a parameter can be enumerated, or it can be injected into the integers. Okay, so, and again, from the definitions, it's pretty clear that this picture increases in Borel complexity. And so here's just the theorem that tells you, so the picture from before, but tells you now that these are maximal with the corresponding potential complexity. So this theorem just says that for all these equivalence relations, E is, for any E, it's potentially d pi 3, then it's in star 3, 1. And you notice, right, there was these little sub-hierarchies, and the maximal one is exactly the maximal one in the sub-hierarchy, right, the maximal index. But the story for today comes from the following theorem. So they have a similar theorem in the same paper, where now let's have some assumption on the group G. Okay, so the same theorem exactly. Yeah, I guess, so I wasn't reading through it, but the picture, focus maybe on the picture. So the same theorem exactly, just now they are assuming that the group that induces the equivalence relation is abelian. And now in all of these cases, we jump from this maximal equivalence relation in the weird hierarchy they defined to the minimal one. So all the right index all drop to 0. And in particular, so if E is potentially d pi 3, it's reducible to this star 3, 1, but if it's induced by an abelian group, then it's reducible to 3, 0. So this is, it fits into a larger picture of trying to understand how simpler groups have simpler actions. And in this case, it's somewhat technical, but you get a clear picture that in these cases, the abelian actions can be classified by simpler invariants. So that's so abelian actions, the orbits can be classified by simpler invariants. And of course, the natural question now is, are these invariants really simpler? And that's the next thing they considered. in many cases, they show that they are. So if you look at alpha plus 3 for any countable ordinal alpha, let's say 4, which is 1 plus 3, then the two upper ones in this sub-hierarchy corresponding to 4 are strictly different. So in particular, the minimal one is strictly Borel below the maximal one, and therefore that's what we wanted in terms of the previous theorem, right? So Abelian actions actually have simpler invariant. But right, there's something missing, so they asked, right, this awkward thing for omega plus 1 and omega plus 2 for some reason. Well, this proof doesn't work. And right, omega plus 1, for example, corresponds to actions which are sigma omega, potentially sigma omega plus 1. So, okay, they asked what about these cases that are left, and in fact, they further conjectured that all these hierarchies are completely strict, right? So also the 4,0 is different than 4,1 and so on. And that's the main theorem I want to talk about. So all of these hierarchies are strict whenever for any beta plus 1 is strictly more complicated than beta. Okay. So now, I guess, well, the question is the proof. I'll mostly now speak about the method of proof, which I'll have to go back to the title, which mentioned symmetric models. So again, a bit of a reminder of what are symmetric models. Luckily, the basic Cohen model was just was introduced the last lecture. It was called the Cohen-Halpern-Levy model. So just to remind you, right, we have some sequence of generic Cohen reals. We have the unordered collection of them, and the definition was up there last lecture. But here's how I want you to think of the basic Cohen model, which I will just write it as V of A, where V is some model we're working over. So you should think of it as the definable closure of A under set theoretic definable operations. So in particular, an important property of the basic Cohen model that we will, or of models of this form, symmetric models of this form, that we will need is that a set is in this model if and only if it's definable from A and some parameters from its definable closure and parameters from B. Parameters from its transitive closure. Sorry. Okay, so how does this relate to Borel reducibility? So quite simply, actually. Here's a short story. We have two equivalence relations. They're both Borel classifiable by countable structures. And so it works in this general kind of setting, but just think of an F as one of these equivalence relations I defined today, the Friedman-Stanley jumps or the weird star equivalence relations. And I told you exactly what their invariants are supposed to be, their definable invariants. So just consider these examples. Now assume we have a Borel reduction from E to F. And work in some generic extension, we have, and suppose there's a set A that looks like an invariant for E, a definable invariant for E. Then what is a Borel reduction? Well, it's supposed to be the notion that captures a definable injective map between E classes and F classes. But right, we use these invariants to definably label the E classes with E invariants and definably label the F classes with F invariants. So a Borel reduction is a definable injective map between E invariants and F invariants. In particular, this E invariant A corresponds to some F invariant B, and since it's definable, then it's in the definable closure of A, and since it's injective, then A is furthermore definable from B, and therefore they have the same definable closure. So that's the story. There's a little bit of an additional consequence here that will be important. So that in fact B is definable using only A, and there is no, remember, an arbitrary set in this model, the transitive closure of A, but this B doesn't. It's just definable simply from A using this Borel reduction. Okay, I don't know if the story, you find it convincing or not, but I mean, this is the main idea, but of course it's not the proof, and the proof relies so sort of on this idea, and almost just on standard absoluteness results, but it actually uses some more modern techniques that appeared in these two books recently of Zaplatal and Kanovi, Sabuk and Zaplatal, but I won't get into the actual proof right now. Let me tell you how it can be used. So here I just have the statement of the theorem again, right? And going back to the basic Cohen model, well, it's exactly the definable closure of an equality plus invariant. but it's not V of R for any R which is an equality on the real invariant, right? An invariant, natural invariant for equality on the real is just a real. Right, it's just it's the classical theorem that L round brackets a set of ordinals always satisfies choice. So since the Cohen model doesn't satisfy choice, it cannot be of this form. And right, due to this theorem, it corresponds that equality. It follows that equality class is not Borel reducible to equality on the real, right? Simply because of this fact. Okay, so great. But okay, this is of course a very trivial irreducibility result. But now, in order to make the connection to these complicated equivalence relations I talked about, so I think of this the basic Cohen set is somehow an invariant that really represents equality plus very well. In this sense, that when you look at the definable closure, it tells you a lot about the equivalence relation, and we need to somehow find good similar invariants that work for these other equivalence relations. And of course. And that turned out to be a really long story, especially to deal with this, the main kind of interesting problem at omega plus 1 and omega plus 2 that but let me at least give you, so a proof of, using these methods, a proof of this irreducibility result, the difference between 3,1 and 3,0. So the point is that this is unlike the previous one, it's a non-trivial irreducibility result. And well, I want to convince you how at least these techniques can be related to these weird star equivalence relations, and also hopefully convince you that these techniques are fairly flexible to changes. So again, we remember this 3,1, the invariants were sets of reals with this definable way of coding them as a single set of reals. Let me just give you the invariant and then try to convince you that it's good in a sense. So what I called before A is now A1, the basic Cohen set. I just want to keep A as the name for the invariant we care about. So let A1 be the basic Cohen model as before. Now, over this model, we can force by finite approximation a single subset, generic subset of the Cohen set, X. Now, let A be the collection of all finite changes of X from elements in A1 in the Cohen set. Then, okay, A is definitely a set of sets of reals, right? And I'm claiming that it's an invariant for star 3,1, just because if you fix a Y in A, then for any other element of A, the symmetric difference is a finite set of reals, and therefore is a real. You can code it as a real. And this map is injective, right? The map sending Z to the symmetric difference between Z and Y is an injective map between A and finite sets of reals, which is essentially the real. Okay, so again, definably uniformly in a parameter from A, we can define injective maps between A and the reals, and therefore it's a star 3,1 invariant. But now to show that it's good enough to get the irreducibility result, we need to show that the symmetric model that corresponds to it. Oh, yeah, so we care now about V of A, right? And just notice that it's the same as the generic extension of the Cohen model, right? Because A is definable in this model, and also X has to be in V of A because it's in A, the transitive closure, and A1 is definable from A because it's the union. So these two models are the same, and we care about this one because of the theorem from before. So what is a 3,0 invariant? It's a set of reals which can be uniformly enumerated, but in particular it's a set of reals which is countable. That's what we're going to care about. So I want to convince you that somehow this model is not generated by a countable sets of reals, which is false, right? Because it's V of a set of two sets of reals, of course. So that's where the subtlety in the previous theorem comes in. If B is also definable using only A and not parameters from A, right? Before X is an element of A, but it's not definable from A, then we can show that B does not generate the whole model, and from the theorem it follows that the irreducibility theorem follows. How long do I have? Oh, great. Oh, good. So I can actually, I think I went kind of faster than I thought. Okay, so how do I convince you of such a thing? So, okay, assume for contradiction that B, there's some countable set of sets of reals B, which is definable again alone from A alone without additional parameters, and it generates the whole model. In particular, the set X, this generic subset of, this interesting generic subset of A1 is in this model. And remember, everything in the model is definable from B, and elements in the transitive closure of B, and parameters from V. Let's first and just think that it's definable from B and one element of B, just to make the notation a bit simpler. So X is defined as the unique solution to this formula. Now, I guess the idea is now I want to translate this, the fact that VA is equal to VB, I want to translate this into some bijection between the elements of A and the elements of B. So, okay, what are the other, some other elements of A are finite changes of X, right? So for any little a in the Cohen set, I can look at the symmetric difference of X with A, and right, I can go between them by applying a permutation of the poset that added X, right? The permutation that changed its X's opinion on one real A. And so what's the point? Okay, I just want to apply this permutation to this statement here and see what happens. Of course, X goes to X delta A, and here also. But here's the crucial point now. So these permutations, by definition, preserve A, because A is of X. So if we change X by finite change, it doesn't change A. And since B is definable from A alone without additional parameters, then these permutations also preserve B, and therefore, right, B here stays the same. And now U is mapped to, under this permutation, is mapped to some element of B, so I'll just call it some U depending on A, which is, again, an element of B because B is preserved. And okay, and right now X, so for any other element of A, which, for any little a, the symmetric difference of X with A is defined as defined by B and some U sub A. But this gives you an injective map between the Cohen set, right? For any little a in the A1, I get you some U of A in B, and it's injective because U of A defines X delta A. So it means that the Cohen set is countable, and that's a contradiction. So that's it. And right, there's a slight thing here that we need to know that, so you know that the Cohen set is not countable. There's no enumeration of the Cohen set in the Cohen model, but we need something stronger. We need that it's not enumerable in the extension of the Cohen model by this set of reals. But this was known in the 60s. It's a standard fact, which, okay, I don't have time to prove now, but it's not too hard. So you can add this subset without, when you add this subset by finite conditions, there's no damage done to the Cohen set. And great, so I guess since I have a minute, I should mention, well, I guess, right, to make the connection, so to make the connection with those other, with the rest of this hierarchy, the star hierarchy, it turns out that once you make the translation and you ask the questions in symmetric models, they are much, much harder than this case, and they are strongly related to recent modern work in choiceless theory that appeared in the work of Karagila and Chayut. And therefore, well, I guess it's a kind of a long story how to get there, but I'll finish here. Thank you.